I've got an Internet of Things test that I'm doing here, and so what I've got on this board here, I've got the Arduino Pro Mini, so this is a 3-volt board, and then there's a radio module which is attached to as well, which is also running off 3 volts. So this is based on the SX1276, so it's a LoRa chip. And so far, testing the software, I've been running it with this. So this is a USB interface so that I can connect it to the Arduino IDE that I'm running on the computer. And this one is capable of 3-volt operation as well. So this has been driving 3 volts into the board. But now I've actually got the software running on this board, and what I want to do next is make this into a self-contained unit. So I need to run it off some kind of battery. So I've got various different types of battery that I could use. I've got various different types of battery that I could use, but this one seems like a nice one for the job because it's very thin, and this is a 3.7 volt type, because some of these batteries are 4.2 volts, and what I want is something which doesn't try and push too much current into these devices because they could be damaged. So and also don't really want to use the regulator on board here, because it basically regulates by turning voltage into heat, so it's actually wasting energy, which won't make the runtime in the field any better. So I got a 3.7 volt battery, and according to the datasheet, so for the LoRa chip here, this will tolerate 3.9 volts according to the datasheet. And although I haven't directly looked up the specs for the Arduino Pro Mini, the 3.3 volt version, I have seen people running it in 4 volt circuits before, so I think it will tolerate it okay. So I'm going to connect this to this, and they make quite a nice pair in terms of physical dimensions. And what I also want to do is I'm going to use this little chip here. So this is a charging board, and so this would allow me to put a USB interface on this battery so that I can charge it using a USB micro, that is, so a micro cable. But the other thing that's really great about this board also has overvoltage, overcharge and over discharge protection. So if you see on the right hand side of the board there's that little chip there, the DW01. So this is a chip that can tell if you're trying to overcharge the battery, and it can also tell when the battery is being deeply depleted. So because with lithium polymer batteries, you shouldn't take them down to absolute zero. You shouldn't really discharge them so that they're totally exhausted, because it damages the battery and you won't be able to use it properly anymore. So the DW01 prevents the battery from becoming deeply discharged. And this package here is a couple of MOSFETs. So this is the actual switch that controls current in and out of the battery. I'll put a link down below, because Julian Eilert did an examination of this board some time ago, and so if you're interested to know these chips and how they work, I'll give you a link to that. So I'm going to solder these things together and get this up and running, and we can do some tests and make sure that it's actually properly sending data into the Internet of Things platform. We don't need any particularly thick wires for this application, because I'm not going to be drawing a lot of current out of this battery. So let's start by putting some colour-coded wires on the battery. Incidentally, this battery came out of an old laptop, so I took apart a laptop battery and took two of these out. It does have a tiny, I think this must be a shunt resistor here. It seems to have a low ohms value, but I decided to leave it in place. It doesn't do any harm. I don't think I need to use it, but I'll leave it there. You can often get good batteries out of an old laptop battery, because sometimes one or two cells will fail, but they'll leave a good one. So I took apart a battery recently which had started to get very bulgy and dangerous looking, and it had two very bulgy and cells that I didn't want to keep, so I took those down to the dump. But the third one I actually kept, and it's a bit thicker than this one, so that'll be useful for some application. I'm going to try and clip one wire at a time with this, because it's not really good to short out these batteries. Okay, so that's the battery terminals in place. And for the link to the Arduino, I thought I'd use a couple of these DuPont connectors. One of these seems to have been covered in epoxy at some stage, but I only need one end. Actually, this positive terminal doesn't need to be that tidy, because these top two are actually connected anyway, because the switching happens between the bottom two terminals. So this is where the MOSFETs switch. There we are. So that's a neat enough job. Now, so we'll connect the negative over here. On the positive goes over here. I just saw an LED come on, so that's a good sign. The USB interface is not fully connected at the moment. I've just disconnected the power lead there. So that's running. So let's see what's happening on the IoT platform. My Internet of Things device is actually sending its data into this platform here, the Things network. So each message that gets sent out from the module ultimately shows up in my console here, and you can see on the screen now there's one message already been received from the platform. The Arduino is currently only sending one message every 7 minutes or so. So the messages don't come up on the console here very rapidly. You just see another one has come up there, so 1349. So this one has the counter set to 15. So each message that gets sent out has a unique counter. So I will probably fast forward this part here because it's going to be a few minutes before the next message arrives. But this is basically the intention. So a battery powered IoT device is going to sit somewhere reading values through a sensor, and every few minutes or so it's going to send in a value to the platform here where we can forward it to a database or ingest it into Amazon Web Services or whatever it is that we want to do with the IoT data. I thought I'd try and measure the current a little bit to get some kind of baseline of what the current consumption is for this circuit. So I've put a shunt resistor in here. I've been measuring the voltage across the shunt, and what I saw when I was testing is that the steady state current was about 21 milliamps, and then at the moment it transmitted it went up to something like 65. It's hard to know exactly what the value was because you just see it for a moment on the multimeter, but let's take 65 as an estimate. But the thing that we need to try and reduce for a self-contained IoT device is this steady state current, because 21 milliamps is quite a lot, and I think we can do better than that because there are a couple of things that we don't actually need on the Arduino. We can take off that red LED, which might be drawing as much as 10 milliamps perhaps. And there's also a regulator on there that we're not using, so we'll whip that off because we're using the 3.9 volts directly from the battery, and that gets rid of any quiescent current that is being drawn by that regulator. The other thing that we can do that I haven't done yet is to actually change the software. So one of the approaches to making batteries last a long time is to actually put the microcontroller to sleep. Now, the way that the program is running at the moment, it's waiting on a software timer, and every 7 minutes or so it sends a reading into the gateway. But the software timer is just spinning around in a loop somewhere, so that's still using a lot of current. So what we need to do is actually wake this up with an interrupt every 7 minutes and allow it to do some processing and then go back to sleep again. And there are ways to do that. So I'll say that for a future video because I'm going to need to do a bit of work integrating some of those ideas into the software that I've got here. But there we go, that's a first look of powering the IoT device as a standalone self-contained unit.